Modern deep learning relies on Boltzmann-Gibbs-Shannon statistics. Softmax cross-entropy Gaussians. This framework assumes additivity and weak correlations. But real-world data violates these assumptions. We see Zipfian token frequencies, long-range dependencies, and heavy-tailed gradient noise. The BGS machinery is rigid. It offers no dial to trade off the influence of rare versus frequent events. Tsallis statistics solves this with a single entropic index, q. It generalizes the framework via pseudo-additivity, capturing correlations that Shannon entropy misses. The core is the Q algebra, the Q logarithm and its inverse, the q-exponential. The q-exponential is the design knob. For q greater than 1, it has a compact support that enforces exact sparsity. This is the mathematical foundation of sparsemax and alpha-entmax, allowing attention distributions to assign exactly 0 probability to irrelevant tokens. In the regime between 1 and 3, this deformation also yields power law tails, creating q-Gaussians that are equivalent to student T distributions, providing robustness to outliers and heavy-tailed priors. For q less than 1, the distribution has compact support, useful for bounded modeling. But why does this structure emerge in AI? Superstatistics provides the dynamical origin. When your system's intensive parameters, like local loss curvature, fluctuate across many batches, the marginal distribution becomes a mixture. If those fluctuations follow a gamma distribution, you recover the q-exponential, with q determined by the relative variance of the fluctuations. This explains the heavy-tailed gradient noise and weight spectra observed in trained networks. They are non-extensive signatures of fluctuating optimization landscapes. The q-central limit theorem formalizes this. Aggregates of correlated signals converge to q-Gaussians, not standard Gaussians. So q is not just a physical curiosity, it's a structural property of learning dynamics. And crucially, q is differentiable. You can optimize it end-to-end. Treat q as a learnable inductive bias. Let the network discover its own sparsity per attention head, or its own tail heaviness per layer. Tsallis statistics unifies sparse attention, robust regularization, and heavy-tailed dynamics into a single, backward-compatible design pattern. It's time to turn the dial.